Yeah, I'm Dr. RameshBabu working in Gotias University. Today we will be finding out the deflection at any point A, that is at a distance A from the left support, and also at a distance B from the right hand side support. We will also determine the rotations or slope at these location, that is point A. We will find out the theta A, and also here at this support B we will find the theta B. So how to find out these deflection at any point as well as theta A and theta B, that we will see in this video. So in this tutorial, you can find that a load P is applied at any distance A from the left hand side support and also at a distance B from the right hand side support. So here we will solve the problem using conjugate beam method. Now first we will take the real beam and we will try to plot the bending moment diagram for this real beam. So to find out the bending moment diagram, first we will calculate the reactions at point A as well as at point B. So for this, let me take moment about this point B. So if you take moment about this point B, summation of all the moments at point B is equal to 0 because this beam is simply supported. No, so you can see that the first equilibrium equation is summation of moment at B is equal to 0. Now coming back to the fundamentals, this reaction at A multiplied by L is creating a clockwise moment. So this moment is clockwise moment. So I have taken it to be positive, and that is being balanced by the load P, which is at a distance B from the right hand side support. So writing the equilibrium equations, you have RA into L minus P multiplied by B is equal to 0. So from this we will calculate the value of RA. Once the value of RA is obtained as PB by L, we will move on to the next equilibrium equation, summation of V equal to 0. So this says that the summation of all the vertical forces acting on the beam is equal to 0. So the reactions RA and RB are acting upwards. So let us take them positive, and the load is acting downwards and take it as negative. Now substitute that in this equation. Already we have calculated the RA. So this RA is substituted in this equation. So once you substitute that, then you simplify this. RB is equal to P minus RA, that is equal to P minus PB by L. Then you simplify it by taking P by L as common multiplied by L minus B. We already know that the fact is A plus L sums up to be the total distance L. So from this you get L minus B equals A. So that is being substituted in this expression. So once you do that, you get RB equal to PA by L. So now I have calculated the reaction RA equal to PB by L and RB equal to PA by L. Now we are ready to find out the bending moment and also draw the bending moment diagram. So here comes the bending moment diagram. Bending moment at point A can be found either from left side or you can find it from the right hand side. Let me prefer it from the left hand side. So the point at point A, which is at a distance A from the left hand side support, the maximum moment is RA multiplied by A. That you can find here, RA multiplied by A. Already we have found out that PB by L is RA and you multiply it with the distance A. So finally after simplification we get the maximum bending moment at this point, and that is nothing but P into AB by L. So PAB upon L is the bending moment diagram. Now whatever calculations we have done is with the respect to real beam. So this is the beam which is concerned for calculation of del A, theta A and theta B. So this beam is also called as the real beam. So I stop here the calculations of real beam. Now we are going to enter into the conjugate beam method. So for conjugate beam method, this PAB by L EI diagram is required. So I assume that the value of Young's modulus of elasticity of the beam is constant, as well as the moment of inertia of the beam is also constant. Now this bending moment diagram will be converted to the load diagram for the conjugate beam. So how will you convert this as load diagram? Let us see. So now we go to conjugate beam method. As per conjugate beam method principle, the simply supported N is always simply supported like that of the real beam. So you take the same beam and convert it to conjugate beam. So note down that this beam is nothing but the conjugate beam. So this is conjugate beam, and we already calculated the maximum bending moment at this location is PAB by LEI. Now after this you convert it to loading. Now you have got a triangular loading which is applied in the conjugate beam. Note down that whatever calculations we are doing, we are going to do is with respect to conjugate beam. So you can see RA dash here and RB dash here. So this RA dash is the reaction of the conjugate beam. This RB dash is the reaction at point B dash of the conjugate beam. And the bending moment of the real beam is the load diagram for the conjugate beam. So this is the load diagram for the conjugate beam, and this beam is called the conjugate beam. Now we will calculate what is the reaction RA dash, what is the reaction RB dash, and also I will determine what is the bending moment at this point A. Let me take this point as A. It's not a big issue. Now this point is taken to be A, and at this point I will calculate the bending moment at A. Now the load diagram is simplified or divided into two portions. This saffron color portion gives you a small triangular loading, and also this blue color triangular portion is also giving you the triangular loading. So the whole triangle has been divided into two right angle triangles, and you can see that the centroid is represented by these red color dots, and these centroid are at a distance 2b by 3 from point B dash, and this centroid of the loading, which is in saffron color, which is a triangle, is at a distance a by 3 plus b. So this is very simple because you can easily calculate the centroidal distance. You can calculate the centroidal distance with respect to B dash or A dash. Here I choose B dash. So for this B dash, the triangular on the triangular loading, I have calculated the centroidal distance. Then proceeding further, what I will do is I will find out the reaction RE dash and RB dash for the conjugate beam. So you can see that from this you take moment about the point B dash is equal to 0. So what you will get is you will get RE dash multiplied by the total distance is L, and then these for the triangular loading you find out the area of the triangle, which is the total load, and multiply it by, first for this triangle it is x1 bar, and here you find out the area of the triangle, which is the total load, multiplied by x2 bar. So this is a simple phenomenon and is explained in the next slide. Now you can see that RA dash into L equal to half multiplied by A into PAB by LEI multiplied by A by 3 plus B. So this is, these terms represents the area of the saffron color triangle, which is the total load. So this is the area of the triangle, which is the load, total load of the saffron color. This is the centroidal distance, which is x2 bar. Similarly, this is the loading of the blue triangle, and this distance is x1 bar. So half into B into PAB. So this is the area of the triangle. Okay, so area of the triangle is the loading. So this is also area of the triangle, which is the loading. Then you multiply it by the centroidal distance. So here you can see that the equilibrium equation is m dash b equal to 0. Now later on you can watch these steps how I have simplified, and finally I end up with the calculation that r dash a equal to PAB by 6 EIL multiplied by L plus B. Once you know RE dash, then you can see that RE dash plus RB dash equal to the area of triangle 1 plus area of triangle. Then you can easily find out what is RB dash. So that is explained in the next slide. Now here, so you have to apply the second equilibrium equation, that is summation of all vertical forces is equal to 0, which will give you the RE dash plus RB dash is equal to half times PAB by LEA multiplied by L. Because you know that the total loading is here, can note down that this is already found as PAB by LEA. Now the triangle is having a length of L and this is height. So you can see that half into this length, you can take it as B. So we know that the area of the triangle is half PH, which is nothing but represented by PAB half into this is height. PAB by LEA is height, and here you have this length is nothing but B. So this is half into B into H. That's the total area of the triangle, which represents the total load. So you are going to calculate the total load acting on the conjugate beam, and that is the total area of the triangle, which is equated to the forces RE dash plus RB dash. So from this you get RB dash. Then upon the simplification is not that much complicated. You replace L by A plus B because the total length is equal to A plus B. Okay, that's known to you. And once you substitute all the values and simplify, finally you get RB dash equal to PAB by 6 EIL into L plus A. So this is how I have found out the reactions for the conjugate beam. So now we have this RA dash and also we have this RB dash. Now let me calculate the bending moment at this location. Okay, so this is the load diagram. This is the load diagram. From this load diagram only we have calculated the RE dash and also the RB dash. Now we want to calculate what is the bending moment at this particular location, which is at resistance A. So how to do that? It's very simple, that you multiply RA and the lever arm distance is A. Then you subtract the moment due to the saffron color triangular loading. So saffron color triangular loading is nothing but area of the triangle. So area of the triangle is half into this small a multiplied by PAB by LEI. So this will give you the loading. Then this distance is the centroidal distance. So that will be nothing but multiplied by A divided by 3. So this is the moment expression for moment at this point due to this triangular loading, and you find out the difference between this moment and also the moment due to RE dash, which will give you the total bending moment. So let's see that now. Now proceeding further, you can see that the bending moment at point A equal to RA dash into A minus half times A into PAB by LEA into, so this is the total area of the triangle. So this area of the triangle is equal to the total loading acting on the conjugate beam. This is the centroidal distance. Now, proceeding further, you simplify this. Very simple. You substitute the value of L as A plus B. So R dash is already known to you. Then you substitute that. And for simplifying, you just introduce L is equal to A plus B. Then finally, you end up with bending moment at A equal to PA square B square by 3EAL. Now the conjugate beam is finished. So for the conjugate beam, we have calculated RA dash, RB dash, and also the bending moment at A. Now this RA dash is the theta A of the real beam, and this RB dash is the theta B of real beam, and this bending moment is nothing but the delta A of the real beam. So proceeding further, you can see that now this is the real beam. So note on that this is the real beam. So coming back to the real beam, we have calculated this delta A, which is equal to the PA square B square by 3A, that is bending moment of the conjugate beam. Then this we want this rotation theta A, and also what is the slope theta B. So that is nothing but RA dash and RB dash of the conjugate beam. So proceeding further, here you have del A of the real beam equal to bending moment A of the conjugate beam. That's calculated. Then theta A of the real beam equal to shear force at A dash of conjugate beam, that is PAB by 6 EAL into L plus B, and theta B of the real beam is PAB by 6 EAL into L plus A. Now summing up the results, these are the results which we have derived. So this is how we derive the expression for deflection under the point load applied at any distance A from the lift support. So once you get this, the next thing is what will happen if you want to have deflection at the middle. For example, let me draw the diagram. So this is the beam, and in this beam you are applying a point load at this location where this is point A, this is length A, and this is length B. Okay, this is length A and this is length B. So A is equal to B equal to L by 2. That you are going to substitute it in this expression, and in this expression, so that you can find out the deflection for the point load applied at the center. So obviously, if you substitute all those things, you will end up with the PLQ by 48 EI. You will get this PLQ by 48 EI for the deflection. So this will be the deflection at this location if you substitute A equal to B equal to L by 2. Similarly, you will get the expression for theta A after substitution of A equal to L by 2 and B is equal to L by 2, as well as you will get theta B. So because since the loading is at the center, the theta A will be equal to theta B. Proceeding further, you can see that these are the values for delta at center, as well as the rotations or slope at these points will be theta A and theta B. That is being calculated and tabulated here, and that will be shown here. So results for A equal to B equal to L by 2, you get del at the center PL cube by 48 EI, and theta A equal to PL square by 16 EI, and theta B equal to PL square by 16 EI. So that's the end of the problem. Here, yeah, that's being explained here in this table. And proceeding further, there's a simple example. Aluminium beam is taken. The span is 0.6 meter. It is simply supported at the points A and B. The width of the beam is 25.3 millimeters and depth of the beam is 3.1 millimeter. Take a small aluminium beam which is having a width of 25.3 millimeters and the depth is 3.1 millimeters. This is the aluminium beam. So you can see that the aluminium beam is taken like this, where the span is 0.6 meters. So this is 0.6 meters. And the Young's modulus of elasticity is 69 GPa. Find the deflection at the center and also find out the theta A. So if you draw the deflection diagram, you need to apply the load at the center. Here, the load is 0.981 Newton. So you have to find out the theta at these locations, and also you have to find out the delta at the center. How to do that? So already we have derived the formula. So as per the formula, you apply the value of length, you apply the value of B, you convert it to meters, and you have E equal to 69 to 10 power 9 pascals, P equal to 0.981 Newton. Find out del center, theta A and theta B. Now, first you calculate moment of inertia, which is very simple, BdQ by 12. Substitute the values of B and D, you end up with this expression 6.28 into 10 power minus 11 meter power 4. Now you substitute A equal to B equal to L by 2. Del at the center is PL cube by 40 EI. So substitute L cube, substitute EI, and finally you get del at the center. The value comes around 1.0186 millimeters. First you get the value in meter, then you convert it to millimeters, and once you get this, the value is around 1.02 millimeters. Okay. Now you want to find out the rotation at the supports. Theta A and theta B equal to PL square by 16 EI. Substitute EI, substitute L, substitute P. So you get a value of theta A equal to theta B equal to 0.00509 radians. So this is how we calculate the theta values and also the deflection. So today we learned how to find out the deflection and also the rotation at any point when the point load is applied at any arbitrary distance from the left hand side support, and also from the right hand side support. So that's the end of the video. Thank you.